Okay, let's get started. So, this is a question from the practice exam. And this is an integration by parts question, but it's one where it's going to work by having the same thing occur twice inside the expressions and putting it on the other side. So if you look at this initially, you might think, okay, it doesn't look too good as an integration by parts, because if I let, the classic choice would be to let v prime be e to the x, because then v is no worse, it's still e to the x, and I differentiate this thing, then I'm going to get e to the x 2 cosine 2x, which doesn't look any better, right? Doesn't look any better, yeah? However, the trick is to do it one more time. If we do it one more time, then we're going to get the same expression back. And again, you might think, okay, well, then we're nowhere. But no, because we'll get the same expression back with a minus sign, which means we can put the same expression on the other side and then actually have an answer for this. So this is just a trick, but it's a very classic trick to test your integration by parts. And that is the actual method to do here. There isn't any other thing to do. It's always a good bet when you have e to the x times something that integration by parts will be a good choice. So let's just do it because it's here and you might see it in whatever, a few hours. So let's, as normal, let v prime be this thing, let u be this thing, and then what do we have? Then v is just e to the x, so we have e to the x, u is this, minus, now v again is e to the x, and now we differentiate this thing, we're going to have a 2, and we're going to have a cosine of 2x dx, right? Which looks no better, but now our problem is to deal with this thing. So we'll deal with this thing separately. So everything in the blue box, like this. And we do the same thing. We're going to let v prime be this guy and u be this guy, right? Let me change color. So v prime is this thing, u is this thing, yeah? And just evaluating what's inside the blue box, what do we get? We're going to get vu, so e to the x, cosine 2x, minus the integral this thing, e to the x, and then we differentiate this thing, we're going to get a minus 2 sine 2x. dx, like this. Yeah? Clean that up a little bit. E to the x, cosine 2x. The minus minus becomes a plus, so we put plus 2 cosine e x sine of 2x dx. And again, that's just the stuff in the blue box. So we're going to find what this original thing is by putting this expression inside. So call this thing star, and then star is this. So we have e to the x sine of 2x minus 2, everything in the blue box. So minus 2, this expression, e to the x cosine 2x, and now this becomes minus 4, right? Okay, and this is good for us because on the left-hand side we have this expression, and we have this minus 4, this expression again. So we can put it all on the left-hand side. We can add 4 integral e to the x sine 2x, and put it all on the left-hand side. You see what I mean? Yeah? Give me a thumbs up if you're following me. Cool. So if we do this, we do 5 e to the x sine of 2x dx. And what do we have left? We have just e to the x sine of 2x minus 2 e to the x cosine of 2x. And we need a plus c, of course. And then we just divide by 5, and then we're all set, right? So I'm just going to rub this off and put 1 over 5 in front of everything. Okay, I'll explain in a second. Thank you for the question. Does that help? Oh, great, thank you. All right, everybody with me? So, it's just 2 iterations are required, and also just to know that you don't, it doesn't look like you've made any progress when you've done this. So the other thing that's required is to know not to give up, just to do it one more time. It's a trick. It's nothing deep here. It's just a trick. But given that it's here, you might see it. You might see it today. So if you see e to the x times sine or cosine, it's going to be whatever we have here, 2x, 5x, whatever, it doesn't matter. E to the x or even e to the 2x times sine, whatever. Just keep doing integration by parts. Do it a second time, and then you'll have minus the thing you want on the other side, and you'll put it all on the same side, and that's going to be your answer. Okay. So if you haven't done a Weber sign question like this, if this doesn't seem natural to you, I mean, hopefully you've done this in the practice exam already. Just run this through. Do an example of this. Make sure you can do it. Yeah. All right. Cool. So that's the extra thing I wanted to show from the practice exam. Now let's do a little summary of what we have learned, because the midterm is just covering what we've learned from the last semester. Sorry, not from last semester, from the beginning of the semester. So, what have we learned? So, we've learned following sections: 7.1, which is integration by parts. We've learned 7.2, which is trig integrals. We've learned 7.3, which is trig substitutions. We've learned 7.4, which is integration of rational functions by partial fractions. So of rationals. And 7.5 is just strategy, which means just putting all these things together. 7.5, strategy for integration. So in effect, we've only learned 4 things, right? We've only learned, or 4 different topics. We've learned this, we've learned this, we've learned this, and we've learned this. That's all we've learned. Yeah. So to absolutely kill this exam, you need to be able to do these 4 different techniques correctly, and that's it. That's all you need. Yeah. All right. So, some of these are easier than others. When we're doing integration by parts, we have to choose the u and the u prime and the v. We have to make a choice. We have to make a smart choice. When we do a okay. Well, I should also say, I should also say that implicit in this is u sub, because we'll need to do u sub as part of this, even though it's not. So let's put it in here. It's last semester's work, but we need to do u sub as well. So when we do integration by parts, we have to make the smart choice. When we do u sub, we have to make the smart choice. When we do the trig integrals, we don't have to make any smart choices, because we just identify it as a trig integral and we just follow the algorithm. Yeah. So this maybe is like lengthy, but this thing, it's hard. If you've practiced this, then it's hard to go wrong. And when you do trig sub, you have to find there's only going to be one trig sub. So again, if you've practiced this, you're going to get it right. And again, for integration of rational functions, there's no choice to be made. You identify the form, and then you just follow the steps 1, 2, 3, or whatever to the end. Again, it's lengthy, but there's nothing other than just identifying the form and just going through the steps without getting it wrong. Yeah? So the only things that require some kind of creative good choice are the u sub and the integration by parts. Yeah? And everything else is just following the algorithm. Just following the algorithm. Just knowing how to do the algorithm and following it. Yeah? So this shouldn't be too difficult a thing, because learning to pick the right u prime v or v prime u and learning to pick the right u sub is just a matter of practice, and that's the only thing where there's some kind of real necessity to think and have your experience, your creativity come into play. All right, let's briefly go over these topics as quickly as we can. So 7.1, integration by parts. So if there is, well, as I already said, the thing that is tricky is to make the right choice of u sub, the right choice of v prime u, and to identify that's a good strategy. So here's an example: 0 to 1, tan to the minus 1 of x, which means arctan, of course, inverse tan function. Here's a good kind of strategy to have in mind. If you're looking at some integral where you don't have any other good ideas, but you notice that this function, you can differentiate it, you know what the derivative is, there's a hint that it might be a good idea to do a u sub. Sorry, I keep saying u sub. Might be a good idea to do integration by parts. Yeah. So if you just see one function and you don't actually have any idea what to do with it, but you do know what the derivative is, good idea to try to do integration by parts and let this thing be u and v prime be 1. Okay. So in many cases, when you do integration by parts, the choice of v prime u will be very easy. So, for example, if you see any kind of function like e to the x and then say x squared, then that's definitely an easy thing to identify as integration by parts. And we're going to let v prime be this thing and u be this thing, because when we integrate e to the x, it doesn't get any worse. And when we differentiate u, it gets better. Yeah? Those things are easy things to identify. This is maybe slightly harder to identify. Yeah, but what I want you to keep in mind is again, that if you can differentiate this thing instead of integrating it, then consider this as 1 times this function, and then differentiate, let the u be this thing and the v prime be the 1. So let's see what happens. So this is, we're going to think of this as 1 times this, and then we're going to let u, put it over here, that we're going to let u be this thing and v prime be the 1. Okay? Because, again, we can differentiate tan to the minus 1. We know it's 1 over 1 plus x squared. Yeah? So this thing is 1 to 0. V is just going to be x. So this is this. And then minus the integral from 0 to 1. And then we integrate this to get x. We differentiate u to get this thing. And now we see we're in good shape, because this thing is now an obvious u sub. Right? Now this is an obvious u sub by letting u be this thing on the bottom. Yeah? Everybody happy? Cool. So this thing is easy to evaluate because what we need to know is arctan of 1. So if theta is equal to, start again, theta is equal to arctan of 1, that's the same as tan of theta is equal to 1. And as we discussed, this is one of our classic triangles, right? This means that the opposite side is the same length as the adjacent side. So we know that this thing is going to be pi over 4, right? This thing is easy to identify. So then we can evaluate this thing. We put in 1 inside this, we're just going to have pi over 4. And we put in 0, we're just going to get 0. And then it's just this thing. Let's try and do the u sub here a little bit. So let's u be x squared plus 1. The u equals 2x dx. So then the x dx structure right here is picked up here. Yeah. We're going to have to change the limits. So when x is equal to 0, we end up with 1. When x is equal to 1, we end up with 2. The x dx is du over 2, so let's put a 1 over 2 right here. And then we just get 1 over u, right? And now we're in good shape because we know the antiderivative of this thing, it's just log absolute value of u. And then I just put it in. Log of 2 minus log of 1, which is just log of 2 because log of 1 is 0, and that's the answer. No? All right, so take away from this just that, again, if you have a function where you're trying to integrate it and you don't know what the integral is, but you do know what the derivative is, integration by parts is a good choice. Another classic example of this is when you're trying to do this thing. We saw this, I think, on Friday. Yeah, we don't know what the integral of this thing obviously is, but we do know what the derivative of log is. Yeah, so we let v prime be 1 and we let u be this thing, and integration by parts turns it into something that we can do. Okay, cool. All right, so that's integration by parts. So raise the board, do some more. Trig integration, that's 7.2. Okay. I claim that this is a fairly straightforward thing because once we see it's a trig integral, then it's just following the algorithm. So there's two kinds. There's either sine to the m. I'm going to write these exponents in capitals because it's probably easier for you to see. Sine to the m of x, cosine to the n of x. And then we have two choices. We either do a u sub with the sine, or do a u sub with the cosine. That's our only two choices. Okay? And then from those two choices, we have to figure out what we need. So in this case, we need to turn everything on this thing into a bunch of sine and then just one cosine left off. Yeah? Because when we let u be this thing, then du by dx is cosine of x, right? So du will be cosine of x dx. So we need a cosine of x dx. Yeah? So how are we going to turn everything here into a whole bunch of sines and just one cosine? Well, we're going to need to pull off one cosine from here, and have all the others be ones that we can turn into sine, which means we're going to need this thing, after we pull off one power, to be an even number. Because if it's an even number, we can use this trig identity, sine squared of x plus cosine squared of x is equal to 1. Yeah? Oh, so it's need. So if we have this, then we need a cosine of x dx, and everything else in sine. As sine of x. Sorry, let me erase this because I have more space. So, need capital N to be odd, which is the same as saying capital N is 2k plus 1. Yeah? Because then we're going to have the integral of sine of m of x. We're going to pull off one power, so then we're going to have cosine squared of x to the capital K, and then cosine of x dx, and then all of this stuff. This identity tells us that cosine squared of x, equals 1 minus sine squared of x, right? So we can just put this thing into this thing, and we are in good shape, right? So it's clear what to do. Now, so if we do this u sub, then we need n, capital N, for the cosine to be odd. Or if we let u be cosine of x, it's the same kind of game. Let me put a line under this stuff. we let u be cosine of x, we need to turn all of this stuff into a bunch of cosines and pull out just one sine. Yeah? Which means that we need m to be odd. Yeah? And if we can't do that, if neither m or m are odd, then we use these formulas that we have. Cosine squared of x equals 1 plus cosine of 2x over 2, and sine squared of x equals 1 minus cosine of 2x over 2, because this thing we can integrate, and so with this thing, so if we have cosine squared or sine squared, we can do it, and if we have cosine to the 4, we're just going to do this twice, and so on. No? So I claim that this stuff, you just see it's of that form, and then there's no other choice than to do these things. Yeah? So you need to remember how to do these things, you need to practice them, but if you have, there's no way to go wrong. Okay, what other options do we have? We can or what other versions, or whatever kind of trig integrals do we have? We have the tan to the m of x sec to the m of x dx. Yeah? And then again, we backwards engineer what we need. So either we let u be, let's start with tan actually, u be tan of x. Yeah, and if so, what happens when we do du by dx? We get du is equal to sec squared of x dx. So we're going to need to have a sec squared of x dx, and then everything else in terms of tan. Yeah, that's what we need. And if we look at this expression, how can we have that? Well, then we need m to be even, because if m is equal to 2k, then we can pull out a sec squared. I keep writing need with an n at the end. Need. And pull out a sec squared from this expression. Let's call this star. Yeah? And then what do we get? We get the integral of tan of x, and then sec of m minus 2, but let's write it already as 2k. So then we have 2k minus 1. Write that better. 2k minus 1 of x, x squared of x dx. And then we have our identity, let's put it over here, that sec squared x equals 1 plus tan squared. Yeah? So then we can turn all of this stuff into tan, because this is just sec squared to the power k minus 1, right? So then this thing here will just become 1 plus tan squared of x to the k minus 1, and we have what we need, because we'll have everything in terms of tan, and then we'll have a sec squared x dx outside. Do you see what I mean? Yeah? Give me a thumbs up if you're with me here. Do this if anything's unclear. Okay, cool. Oh, also put here in the chat so I can see how many of you are here. All right, what's the other option? The other option is u is equal to sec of x. And again, we ask ourselves what we need. Well, if we do this, we're going to get sec of x, tan of x. Yeah, so we're going to have to pull out a sec of x, tan of x from star, and then have everything else in terms of sec. Yeah? And how can we do that? Well, if we do that, what do we need? We pull out a sec of x and a tan of x from this stuff, and have everything else in terms of sec, then we're going to have a tan to the n minus 1 that we need to turn in terms of sec. Yeah? Yeah? And we can do that if n minus 1 is actually an even power. Yeah? Which would mean that n would have to be an odd power. Yeah? So if n equals 2k plus 1, an odd power, we also need that m has to be bigger or equal to 1 because we need to pull out at least one power, right? And m is bigger than equal to 1, then we can turn star into the integral of, remember, n is 2k plus 1, so when I pull out one power, I'm going to have tan squared of x to the power k. Yeah. I'm going to have one less power of sec, and I'm going to have sec of x, tan of x, dx. Yeah? And then we're in good shape because we have exactly this. This is what we have, this is what we have, and we need to turn all of these guys into sec, and we can do it because of this identity. We have that tan squared of x is equal to sec squared of x minus 1. So this thing goes into this thing, and this is this identity. This is sec squared of x minus 1 to the k. So we have everything in terms of sec, and then sec tan, which is what we want to do this u sub, and we're all good. Yeah, we're all good. Cool. So that's all you need to know, and it just makes sense backwards engineering from the different kinds of u sub that you have to do. Yeah. So how can you get this wrong? You can make an algebraic mistake, of course, but otherwise, or just not know what to do. But I claim that it's not hard to know what to do because you can just figure it out, right? You know, you can just figure it out. And once you've gone through this, best way to do this is to just backwards engineer it from asking yourself, if I have a sine, cosine, and I want to do this u sub, what do I need? If I have a sine, cosine, and I have this u sub, what do I need? If I have a sec tan and I have this u sub, what do I need? If I have a sec tan and I want to do this u sub, what do I need? If you do that, just take a blank sheet of paper and figure it out, each of these cases, you'll have this in your head and you'll be confident about it, and it'll be okay. It'll be good. And just practice sometimes and it's fine, okay? This stuff should be, it can be lengthy, but it should be straightforward. Everybody okay? Everybody good? All right, super. Let's go on to the next section. Okay, trig subs are good for us when we have expressions like this. Square root of either plus or minus a squared, and then either plus or minus x squared. If you see something like this in your integral, then a good guess is that we have a trig sub in play, right? And the main thing to be able to do is to figure out which trig sub we have. So we have two identities. We have sine squared of x plus cosine squared of x equals 1. And we have x squared of x equals 1 plus tan squared of x. Yeah? And let's figure out which u sub we have in play. So if this is the integral, let's suppose we have something like this, square root of a squared minus x squared. Well, if we have something like this, we want to see what structure does something like this. If we look at this guy, then if we let sine squared of x, this is the same as 1 minus cosine squared of x, or the other way around. Let's do cosine. Cosine. Cosine squared of x equals 1 minus sine squared of x, like this. And we see this structure right here, right? We see this structure right here. And the point is that when we take a square root around this, then we'll get rid of the square root because we have a cosine squared. That's the whole point of this stuff, is to deal with these difficult things, the square root. So the good choice here is to use this structure and let x be equal to a sine of x, just because we see it's going to do something good for us. Yeah? So this is the sub. All right. Next guy, what if we have, like this? What if we have the square root of x squared minus a squared? Yeah. So we look at our things right here, and then what is helpful for us? Well, if we look at this thing over here, if we pull out minus 1, we're going to have sec squared of x minus 1 equals tan squared of x, like this. Yeah? So if we let x be sec of x, we see this structure here, right? And then when we do the square root, we're gonna have square root of tan squared, which is what we want. So if we let x be this thing, a times sec of x, it's gonna work out well. Next guy. If we have something like this, x squared plus a squared. Okay, again, we look at our identities, we see what we have in play. We see we have this structure right here, right? So if we let a be this thing and x squared be this thing, we are in good shape, right? So then we're going to let x be a times tan of x, right? So the right choice is clear from the identities we have to play with, right? Yeah. So having made the right choice, then it's just a matter of not messing up. You're going to get the answer in terms of some trig integral, and then you're going to turn the trig integral back into something in terms of x by doing the triangle that represents the substitution. Here is a little subtlety that you can sometimes see. So this is example 7 from the book, where it's slightly hidden that it's of this form. So we have something like this. Oops, minus x squared. We have something like this. And the trick is to identify that you can write this quadratic in the form of something like this by completing the square. So what do we notice? We notice that if we have x plus 1 squared, we're going to have x squared plus 2x plus 1. Yeah. So then that means that x squared plus 2x equals x squared plus 1 minus 1, just putting the minus 1 on the other side. So then this thing, we can write it like this. So let's write this as minus this plus this, minus. Yeah? So then this thing is this thing is this thing. Yeah? So then this integral is of the form x over the square root of 3 minus this thing. So 3 minus minus 1 is plus 1, so it's going to be 4 minus x squared plus 1 dx. Yeah? And this x squared plus 1, we can just call u. So it's what I call, what everybody calls actually, a linear change of variables. It's a very easy change of variables because the du is very close to the dx. In this case, it's the same thing. So if we just let u be x plus 1, then du is just equal to dx. So then we can rewrite this integral. We're going to turn this guy. So from this, we have that u minus 1 is equal to x. So then we're going to have u minus 1 over the square root of 4, oops, this should have been squared, minus u squared du. Yeah? And now it's clearly of the form that we want, right? So let's put this in brackets. I'll just put a line on it. And we could further break this up like this. Yeah? Okay. Why did I do that? Why did I want to do this step? Perfect, yeah. So this guy is a u sub, right? Because we're just well, that's what we call it u. We're going to call it w. If we let w be this thing, then dw by dx, we're going to pick up the u du, and this guy right here is not going to be a problem. We can handle this guy pretty easily, right? So we separate off the part that we can handle. This guy, as the guy who answered said, you can, if you've learned your derivatives of your arc trig functions well enough, you'll identify this guy. But we're not going to do that because we're going to use this as an example to practice this trig sub. We're going to get to the same answer. But that's a quick way to know what the answer is. If we take the derivative of arc sine, we're going to have 1 over 1 minus x squared, which is something we can turn into this form. So that's another way to do this. But this is an example for us of u sub. So let's leave this guy. We can figure out this guy. Let's just figure out this guy with a trig sub. So from now on, our job is to do this. Yep. So the thing in the red box is here, and we're going to identify. We're going to make the right choice of trig sub. So let's look at our table right here. What thing on the table do we see? We see it's this thing, right? It's this thing. It's not this thing and this thing. It's this thing. Yeah? Which means our u sub is going to have to be a sine, and we're going to let u, or I should say our trig sub is going to be a sine, and we're going to let u be 2 sine of x. Yeah? Could you just see that this is the right form? Are you with me? Yeah? Cool. So this guy right here, we're gonna, let's put it down here. We're gonna let u be 2 sine of x. We can actually, let's call it theta, just out of consistency, because we called it theta the first time. So u is 2 sine theta, then du by d theta is equal to 2 cosine of theta. And then this thing right here, we're going to turn into an integral in terms of theta. So then this thing is going to be 1 over the square root of 4. Now this thing is now going to be minus 4 sine squared of theta, like this. And our du becomes 2 cosine of theta d theta, right? Box around this. So that's where we are. Let's pull out a 4 from the square root. It's going to kill the 2. So we're going to have integral of cosine of theta. And then this will be 1 minus sine squared square rooted, which we see from this identity is just cosine. So we have cosine over cosine of theta d theta, and then that's just 1. So then this thing is just, the antiderivative of 1 is just theta plus constant c. But that's not the actual answer we want, because we have to get things back in terms of x. So this is our u sub right here. We're going to draw a triangle that represents, again, this is our trig sub right here. We're going to draw a triangle that represents this thing to firstly get it back in terms of u. Yeah? So this thing, it's got to be represented by a triangle, right? So this thing is the same as saying that sine of theta. Can you see this blue color? Is this clear enough for you? Yeah, good. This thing is equal to u over 2, right? So let's represent this as a triangle. So this is our triangle. This is our angle right here. Yep. And what is sine? It is the opposite side, u, over the hypotenuse, which is 2 right here. Yeah. So then what can this thing possibly be? This thing has to be 2 squared minus 4, which is 4 minus u squared. Because when we square this plus this thing squared, we get this thing squared. Yeah? Yeah? So that is everything we can possibly know about this triangle. But in this case, I mean, that's kind of overkill, because in this case, what we need is just theta. So in general problem, we might have something like cosine of theta, tan of theta, or something like this, and then we could just read it off. We just read it off from this thing. In this case, we don't. It's just fallen out so conveniently, it just happens to be theta. So we can just write this as, I mean, this is all that we can do. We can write this as arc sine of u over 2. So we don't strictly need this, but this is a step that you will do in general. You'll get some trig function of theta out, and then you need to unwrap it in terms of your x, or in this case, your u, via something like this. Huh? So this thing tells us this. So we're going to write this thing over here as arcsine of u over 2 plus constant c. Yeah. And then we're going to put this back in terms of x. So then this thing is arcsine of x plus 1 over 2 plus constant c. So the guy who suggested we use the arcsine over here, we could have got the same answer by just factoring out this 4 from outside from the square root and then pulling it all the way out, and then just using the fact that that would mean it would have this arcsine right here, just because we know that the derivative of arcsine is 1 over square root of 1 minus x squared, or 1 minus theta squared. Yeah? Cool, so this is the blue thing. This is this guy here, or sorry, the red thing that we want to understand, right? This is the guy that was giving us a problem, and now we have the answer. Yeah? And the last thing is just to do this guy, but it's just a straightforward u sub, and we can get the answer out of this as well. Okay, so let's go back and see what we did. We had something that looked kind of weird, like this thing. Wasn't obviously identifiable as a trig sub, but it was a square root of a quadratic underneath. So a good thing to try is to see if you can complete the square and get something like this. Yeah. And if you can, then a natural thing is a u sub, so we get this, and now we're in the territory of doing a trig sub. Yeah? Then we identify what trig sub we want to use, what substitution. We look at this, we look at our board, we see it's got to be a sine, so we did this. We let, where is it? We let u be this thing. Yeah? So we turn this into a trig integral, turned out to be a very simple trig integral, it's just the integral of just 1. So the answer is theta. Yeah? Normally the answer would be some trigonomic function, sine, cosine, tan, whatever, sec of theta. Yeah? Doesn't matter what it is because we know what that is, because we can draw a triangle that represents the substitution, and then we can just read off everything else. Any trig function applied to this angle, we can read it off from the triangle. So we can turn the answer in terms of theta into the answer in terms of u, and then the answer in terms of x. So it's a lengthy story, but it's not one where there's any choice to make, right? All you need to do this is to identify it's a trig sub question, and then you just go in a straight line. There's no wrong turning to make anywhere. Yeah? So I claim that this trig sub stuff is, again, lengthy but straightforward. Yeah? Cool. All right, how are we for time? We just ran out of time. Okay, let me see. Okay, yeah. All right. So I want to start my office hour on time. So let's wrap it up for today. Good luck to everybody on the exam later this afternoon. Keep studying. If you have any final questions, stick around because I have office hour now, and we can talk about anything that concerns you. All right. Bye-bye, people. Integral of 8 sec theta tan theta sec squared theta minus sec theta, like this. So have you tried u is equal to sec theta? So du is equal to sec theta tan theta, the theta, and then this guy then star becomes the integral of 1 over u squared minus u du, and now we are in good shape, right? Because this is now just a rational function, so we can, this has to be, this is distinct linear factors, so a over u plus b over u Yeah? Oh, sorry, u minus 1. And then we make a common factor like this. Over u minus 1. And then this implies that one is equal to a of u minus 1 plus b of u, which implies that, which is the same as a plus b is equal to u, and then we're going to have just minus a. So then this implies that a plus b is equal to 0, and minus a is equal to 1. So it implies that a is equal to minus 1, and therefore b is equal to 1. So then this guy over here, 1 over u minus 1, is going to be minus 1 over u plus 1 over u minus 1, and then we know what it is, right? So then this thing, we've called it star already, so star is equal to 8 times minus natural log of u plus natural log of u minus 1, and then we turned it back into sec, so we're going to have 8 of, let's put the minus 8 log of sec of theta, and then plus 8 log of sec of theta minus 1. Yeah? And that should, and plus constant c. And that should be it. Yeah. Yeah. Mm-hmm. Mm-hmm. Yeah, I see. Yeah. Well, it looks like it works, right? So, okay, so let's get to the answer. So then this thing star integral of 1 over u, which is equal to 8 log of 1 minus cosine of theta plus constant c. This thing is equal to 8 of log of sec of theta minus 1 over sec of theta, right? Plus constant, and it simplifies to that, yeah.